Just so you know, the problem we just did a minute ago about heights of men that was up here, that's a problem I really do like to give. So that kind of thing. I'll give you the mean and the standard deviation, and I'll say what percentage is between these two. And you just have to remember 68, 95, 99.7. What distribution does that work for, though? What's it got to be?
Normal.
Normal. If I don't say it's normal, we don't know anything. We don't have a clue where anything is. Okay. So what we're going to get into now is something that I know you guys have come in with some understanding about. And my little brother, he's funny. I got to tell the story. Humans are not hardwired for probability because a lot of it's very counterintuitive. So my little brother, I love him to death, but he still asks me if I teach probability. And I'm like, of course I do, James. And he says, well, all right. All the probabilities are 50-50, man. It's either going to happen or it ain't. I'm like, hey, Jim, I'm so happy you didn't become a doctor, man. I don't want to go in, Doc, what are my chances? 50-50. No. Tell me. So the problem is people misuse probability all the time. Does anyone ever play the lottery? Okay. Every once in a while. And I tell you, I do believe it is a tax on people that don't understand probability. But I'll play every now and again. Why the hell not? Just because. If it's a choice between bread or a lottery ticket, you should probably get the damn bread. But,
To each their own.
Yeah. Shoot, now I forgot my point with that. I go too much on a tangent.
Probability, 50-50.
Yeah, probability.
Happens or doesn't.
No. All right, I'll get there. Probability is not hardwired. It's not 50-50 because what is it based on? What is probability actually based on? So anybody in here left-handed? Anybody? All right. So if I wanted to know, I'm sorry, I'm going to stare at you for a minute. If I wanted to know the percentage of people, the probability that I pick somebody in this room and they are left-handed, can we calculate that?
Yes.
How many people are in this room? Let's see, 6, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. How do we figure out the probability that if I pick somebody at random, I get a left-handed person? How many people are left-handed in here?
1.
Out of?
20.
So probability is all about, I don't care a shit what kind of probability we're calculating, it always comes to this definition. Probability of an event, let's say event A, is the number of things that match what we're looking for. So in that case, I'm looking for a left-handed person. How many things match that? 1. Out of the total number of things that could happen. So it's always a ratio. It's a part divided by a whole. It's the number of things that matches what I'm looking for divided by the total number of things that could happen. So if I pick one person at random from this room, there's 20 things it could possibly be. And only one of them match what I'm looking for. So that'd be 1. In this case, the probability left-handed, 1 out of 20, which is 5%. I love it. You guys can't see that, but it's 5%. All right, I think I'll stick on this board here. That might be easier. Dooby-dooby-doo. There, now you guys can see it. Okay. So right with me, we're going to learn a lot of probability formulas. I'm going to try to show you how they basically come back to the same idea, always. So let's do this. One of my favorite kinds of problems to give is something called a contingency table. The minute I draw it, you're all going to know exactly what the hell that is, right? I'm going to take this away. So let's say I talk to a bunch of people, and there's some people that are less than 21 years old, and there's some people that are greater than equal to 21 years old. Is everybody with me? Okay, I like it. And some say yes, some say no, some say maybe. Okay? I don't know what the question was I asked. You can imagine one if you want. So let's say 7 of these people say yes, and 18 of these people say yes. 21 of these people say no, and 4 of these people say no, and then we'll say 3 and 5. Why not? So this is what's called a contingency table. Contingent on which one of these, it changes the number of each of these. That's roughly where that name comes from. This is set up beautifully for probabilities. What if I want to know the probability that if I pick one person, what's the probability that the person is less than 21 and, no, it's just less than 21. Let's not get crazy, Jeff. What should I calculate first when I see this kind of problem? What should I kind of calculate before I even try to do any probabilities? Considering probabilities are all about the total number that match things divided by the total amount there is.
The total amount of people that are under 21 and the total amount of people that we're sampling, period.
So we can kind of do this. What's the total number of people less than 21?
31,
31, keep going.
58 total. Well, 27.
27. How many total people said yes?
25.
25, that's neat, 8. So I got 58. So that's 58 and that's 58. What if I put 116? Do you understand why somebody might put 116? Don't put 116. Don't do that. Why would somebody put 116?
They totaled it.
They saw 58 people there and they went, oh, there's 58 people there, but these 58 people are these 58 people. Is that? Okay, good. I just want to make sure that mistake doesn't happen. That's a nice check. This must equal the same as that because it's all the same people. I already forgot what it was, 58. Okay. So, what is the probability I pick somebody less than 21? How many people match what I'm looking for?
31.
31. 31 people match that out of 58.
53.45%.
Point, say it, 5?
0.5345.
4 or 5? Okay. Does that look right? Anybody else trying that out? Let me stop. Let me just stop. Is everybody? If I give you a table, I will pretty much always give you these blank boxes on the outside just to kind of jog your memory. You should add everything up. Because if I just add everything up, if I'm able to count everything in a problem, probabilities are easy as hell. They are just the number of the match what I'm looking for divided by the total. I love it. So what about this? So I want probabilities, real quick, there's a reason for this. I want probabilities 4 decimal places. And then you can make it 53.45% if you want to. So there's over a half of the people are under 21, so that's why I have a higher chance of getting somebody who's under 21. Okay. What's the probability somebody said yes or they said maybe? Just apply the idea. What's up?
33 out of 58.
Yeah. How many people match that? Well, all the yeses match it. And all the maybes match it, yes? So how many total people match that? 25 plus 8? 33. Is that all right? So again, probability always comes down to the total number that matches what I'm looking for. Why do I get a bigger number here? Because I said or. I'm letting more things in. 33 out of 58.
0.5690.
Okay. Okay, lock it. Now nobody's saying anything. Everybody think about this. What's the probability that I get somebody who said no and they are at least 21? Don't say anything, just think about it. All right. So what kind of person am I looking for? the person must have done what?
Said no. And be at least.
And they have to be at least 21, right? Do you see how that's more restrictive? They have to match both things. So how many people match both of those?
4.
Yeah, no and 21, greater than or equal to 21. 4 people match both. So we sometimes call we sometimes call it intersection. Do you see why that makes sense? What's the intersection of no and at least 21? 4. 4 people match both things. So let me talk about and or real quick. You got a really silly example. Say you go to a bar, one of those bars that have the little rope thing, you gotta wait outside, there's some guy with a little clipboard, and you're like, oh, come on, let me in. So I come up to the guy, and I'm like, hey, can I go in the bar? And the guy looks at me, all right, 3 things. You gotta know Joe the bartender. I'm like, I know Joe. Hey, Joe, how you doing, man? All right, I can go in. And you have to dress nice. And I'm like, stop right. And you gotta have a lot of money. Well, shit, I'm out. I'm gone, right? And is restrictive and lets less people in. And will always make the number smaller than it would have been without it. So the and bouncer is the mean bouncer, right? Does not let as many people. The or bouncer, so I come up with the or bouncer. Hey man, how you doing? You gotta know Joe the bartender. Oh, hey Joe, I know Joe. Or you gotta dress nice. It's all right, I know Joe. Or you gotta be rich. I'm not, but it's okay because I know Joe. So I can go in. I can meet any of the requirements and I'm in. You guys with me? So you gotta know Joe. Okay. I really want this to make sense. Do you notice how we haven't done any formulas yet? If I give you all the numbers, if I give you everything you need to count, I don't need a frickin' formula. The idea of probability is very straightforward. It's the number that matches what I'm looking for, divided by the total number of things it could be. We are going to develop formulas. We are going to need formulas for cases where I don't give you everything. Okay, so what was this one here? This would be
0.0690. 4 divided by 58.
4 out of
58.
58.
0.0690.
All right, sounds great. We'll crowdsource this. So you guys can all check if you want to. Or you all just take Robert's word for it. Okay, yeah. Notice how the number will always be 58 if I don't know anything about the person. What do I mean? What if I told you this? What's the probability I pick somebody who said maybe, given that they are less than 21? What do I know about the person? Did you hear how I said that? The probability that they said maybe, given that they're less than 21. How many people are we talking about?
3.
No. What's the only thing I know about the person? I know something about the person. This is new. None of these first 3 told me shit about the person. The probability they're less than 21. The probability they said this. The probability they said that. Right? This is the first time I'm telling you something. What kind of person could it be?
They're less than
They have to be less than 21. I'm given that it's somebody less than 21. So how many people total are we talking about?
31.
31 people, right? The bottom is always the total number of people it could be. So the only time the bottom won't be the total is if I give you information. I can throw some people out. All the people that are older than 21, get out of here. Some kind of weird Logan's Run thing. Get out of here. Nobody gets that reference. Out of 31 people. Now again, who did we throw out?
Anyone over 21.
All these people. So who's the only people that we're looking at?
Under 21.
Those people. So how many said maybe? 3. So you can literally cover this on your paper or whatever. When it's a given, you can just cover everything else. So this will be 3 out of 31, which is like 0.0968. Sure. Okay. How are we feeling? So the bottom will always be the total unless I tell you something about it. So if I have a card out of a normal deck of cards, how many cards in a normal deck of cards? 52. So it could be any 50. If I said oh, this card is black. How many cards could it be? 26, right? Half of the deck is black, 26. Are you with me? The only time the bottom will change is if I give you information. Okay, maybe. Let's do one more given, and then we'll talk about the formulas for these things. What's the probability that somebody is at least 21 given they said no? First thing I would think about is what the bottom is going to be.
8.
Yeah, well, no. Given they said no,
Yeah.
25 said no.
Oh, no, I'm looking at maybe, I'm sorry.
That's all right. You guys with me? So I know the bottom's going to be 25. Out of those 25, how many are at least 21?
4.
4. And that one's a nice one. 0.16.
Isn't the bottom 27?
Why?
Because it says.
What did I give us? I really want, I appreciate this, okay. The probability that they're at least 21, given they said no. So what do I know about the person? No, the probability that they're at least 21, given that they said no. So what do I know about the person?
They said no.
They said no. Given that they said no. So what information was I given about the person? They said no. So how many people said no? 25. I really want this to make sense. Whatever I'm given this. So I know I'm only talking about those people. So how many people could it be? 25. There's only 25 people that said no. So again, why was this 31? Are you good with this one being 31? Why? Why are you okay with that? Given they're less than 21. 31 people are less than 21, right? Oh shit. What'd you do? I destroyed us all. I just unplugged this, so all my, shites. All right, everything just went down. I love it. This room was not really well thought out. So whatever this is, whatever I'm given is going to tell me what the bottom is going to be, because that's the total number of people that I could be talking about. So I'm given that they said no. So how many people could I be talking about? 25. Okay. I like it. Yes.
This one, a couple seconds ago, I just want to make sure I have this right. You said only time the bottom will change is when information is given, correct?
Yes, the only time the bottom will change, the only time the bottom won't be the whole amount is if I give you information about the person or thing and we're looking for it. Yeah. Okay, maybe. Okay, so let's do this. Let's talk about the formulas for some of these things. Look at OR, probability of A or B. You know in algebra how we use X and Y? These are standard variables, yes. In probability, we use capital A, capital B, so forth for events. So A could be they said no, and B could be they are at least 21, right? They're just different events. Okay. How did we get 33 here?
We sum the amount that answered yes and the amount that answered maybe. So we summed 25
Yes.
and 8.
25 and 8. I love it. Right? So it seems as if this should be A plus B. Right? There's one thing that's not quite right there. So let's do one more problem. But let's do problem number 6. What's the probability somebody is less than 21 or they said yes? So they could be less than 21, so we're talking about how many people so far?
7.
31.
They could be less than 21, so that's 31 people. Or they could say yes.
18, so 49.
Okay. So you just did something interesting.
7.
Didn't 31 people less than 21 yes?
Yeah.
And then 25 people said yes? But why would it be wrong to do 31 plus 25?
There's overlap between people.
Yeah, if I add these 25 people to these 31 people, who did I count twice?
7.
21, less than 21-year-olds that answered yes.
The 7, right? You guys with me? So, in general, what we do is, it's probability of A plus the probability of B minus anybody who's both. If I count everybody who's in A plus everybody who's in B, anybody who's in both, I counted twice. So if I do 31 plus 25 minus 7, right? 31 plus 25 minus 7, I'll get the actual right answer. So that'll be 56 minus 7 is 49 out of 58. Or, you can be smart about it, 31, how many, if I count these 31 people, how many people said yes that I haven't counted yet?
18,
These 18. And what's 31 plus 18?
49.
Still 49. So there's kind of two different ways. The math doesn't care. And you're all like, I know math doesn't care. Doesn't care about me. Okay. And then whatever that is, 49 divided by 58.
0.8448.
Okay. So one formula we have so far for any or question is this. Now, let me ask you this. When we did this problem, did I subtract anything? When we did this problem? We did yes or maybe. Did we have to subtract anything?
Technically, yes.
No. So, I see what you mean. But we didn't. We subtracted nothing because the only people we have to subtract is anybody who's in both. If you said yes, could you also have said maybe to that one question?
No.
No. You either said yes or you said maybe, correct? Are you with me? So there was nobody who did both of these. That's why I didn't have to subtract anybody off on there. Okay. So one thing I want you to realize, we answered every question about this setup without any formulas. The funny thing is, we are constructing the formulas based on what the hell we did. So if I give you a problem like this, do you have to use the formula? No. You can just count what you need. We'll do another problem later that you need to use the formula because they don't give you everything. Okay? Maybe. So let's look at given. Let's look at the given over there. Let's figure out what the formula is for given. Let me see. Yeah, let me do this. I'm going to erase. Has everybody got all this here? I'm going to leave this one up here. We're going to look at it and see what the hell we did. Okay. You work? Yes. Sorry. Okay. So if I want to know what's the formula in general, what's the formula for A given B? In each of these cases, what told me what the bottom was going to be?
What you're given.
Whatever I'm given. So on the bottom is going to go stuff about B, because that's what we know. Now, was that 3? Was that the total number of maybes?
No.
Nope. Was that 4? Was that the total number of at least 21s?
No.
No. What was it in each case, actually? What was the 3?
The probability that it was A and B.
Yeah, the and.
B,
The
as
and
well
of
as
these
A.
two. Yeah. So the formula is for A given B. I know that B happened, and then I'm going to count all the A's that are in B. So let me give you a visual of this. Have you guys seen this kind of picture before? It's called a Venn diagram. So let me tell you this. I give you, so this could be man and Democrat, for example, whatever, right? It could be whatever. So I tell you that I picked a Democrat. What is the only way that it could also be a man?
There was a male Democrat.
Where do they have to be on the picture? Could this have been?
In the middle where it's intersected, where it overlaps.
True. All right. So these are the Democrats. If I know I have a Democrat, the only way it could also be a man is if it's in here. And that, of course, would be A and B. That's the intersection of those two. In fact, I mean, if I give you any picture, likes broccoli, has a trampoline. Who are these people?
The ones that like broccoli and trampolines.
So that's the and. Okay, I like it. So again, I want you to notice what just happened. This is something you're not used to. We answered a whole bunch of probability questions, no formulas, we just applied the idea. The total that matches what I'm looking for, divided by the total number of things. And then, from what we did, we actually just determined 2 formulas that I can use in case I don't have a problem where I know everything. Okay, all right, I like it. Sort of, maybe? Okay. I'm gonna erase all this. Then we'll sort of review what we've done so far, and then I'll give you an example of a problem that you have to use a formula for. Okay. There's one equation we haven't done yet. We've done or, we've done given. What's the one we haven't done yet? And. I love it. You're going to summarize what we know. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. We just don't want to count anybody twice, right? Vote early, vote often. Can't count your vote more than once. Probability of A. Let me give you the symbol for this. A straight up and down line like that means given. Symbol kind of sucks a bit because it makes people think you're supposed to divide A by B, but no. This is, the given thing goes on the bottom, and then the and goes on the top. Okay. So if, for example, if I give you, let me see, the probability of A given B is 0.2. The probability of B is, you can do it, Jeff, 0.9. Can somebody figure out what the probability of A and B would be?
Yes.
Yeah.
Hold on, just think about it. If you know, do it. Then sit on your answer for a bit. Obviously, which formula am I going to use? I only know 2 at the moment.
Probability of A given B.
Yeah, because this one, there's a whole bunch of stuff I don't know, right? This one, I know 2 of the 3 things. So what does that feel like? Algebra, right? So you can actually plug stuff in. So this is 0.2. This is the stored algebra. This I don't know. It's kind of like my variable. Probability B I give us is 0.9.
Just multiply by 0.9 on both.
Yeah, it's just multiply 0.9. So what do you get?
0.18.
1.8. Okay. If you're paying attention, we just figured out the formula for and.
It is the.
Hold on, we'll get there. So again, this is a new situation, correct? This has nothing to do with that box I just put up, nothing, because it's A's and B's, not M's and Y's and whatever. And we don't have, how many things are there in B? I don't freaking know. I just know the probability of it happening is 90% chance. That's all I know. So I need to use a formula to calculate something like that. I don't have all the numbers to actually set up the ratio. You guys with me? Okay. I should bring some coffee. We're all a little tired. Understand? Okay. You're all like, this is riveting, Jeff. So riveting. Okay. So the formula for and from what we just did in fact, you can look at it right here. If you look at this algebra here, if I just multiply both sides by P of B, peanut butter, if I just multiply both sides by that, I get my formula for and. So the A and B is probability of B times probability of A given B. Here's where people, all right. I was about to say here's where people kind of like lose me in the middle. Dude, I'm way ahead of you. All right. There's an alternate way to write this because, let me ask you this. Okay.
Oh, it's just,
We'll get there. Okay, so there will be problems where I will only tell you the probability of things, and I'll say find this, and then you got to figure out which formula to use. And I will let you use formula sheets. So one thing we'll do tomorrow is we'll create together the formula sheet you can use for the first test. Okay. Yeah. Let me ask you this. Can somebody tell me what this is?
Probability of B given A.
True. All right. So we know the probability of A given B is this formula here, right? Let me take this away for the moment. A given B is this formula here. So for this formula, what's going to be on the bottom now?
A.
Probability of A, I love it. And what's going to be on the top, just going by the,
B and A.
which is the same as
A and B.
A and B, right? I really understand how you're not as excited about this as I am. I totally get it, right? But we're constructing these formulas, which to me, of course, I'm a math guy, so I'm like, oh, look at the formulas. But it's really neat because they all come from an idea. They all come from a concept, and all formulas do is it allows us to capture concepts in a much more concise manner. And that's why we kind of lose touch with them so quickly. It's because they're not the concept itself. It's just some representation. Like, oh, shit's all this number. So if I multiply both sides by this, I actually get another formulation for A and B. I get probability of A times probability of B given A. Now let me make an observation, and then I'll show you an example of something about why and here's the observation. And is basically multiplied, you guys, right? Or is basically add. Why do I say basically? Because here I might have to subtract something sometimes, and here it's not just B times A. It's probably B times probably A given B. I have to change that other one. Okay. But and is basically multiply, or is basically add. That kind of confirms or makes things bigger, right? The or bouncer let more people in, correct? The and bouncer let fewer people in. Let me ask you this. When I multiply two numbers together, it normally gets bigger, correct? 2 times 4 is 8, holy shit. Bigger than 2, bigger than 4. If I multiply two numbers that are both less than 1,
They get smaller.
they get smaller. Yes? What's 0.25 times 0.25? Well, it's a fourth of a fourth. It's a 16th, which is about like 6% or something. I don't know if you guys understand. So what's 0.5 times 0.8? Half of 0.8. 0.4. 0.5, 0.8 becomes 0.4. The answer always comes smaller. So and is basically multiply, which jives with our understanding. The and bouncer lets less and less people in. So real quick, one more story. Because I'm an old man, we like to tell stories. When I was in college, have any of you guys ever applied for scholarships? Anybody considering applying for scholarships? Nowadays it's all digital, correct? Okay, back in my day, I could climb uphill, we had a financial aid office, you go inside the financial office, and it's, hey, how you doing? Hey. And there's this book, it was literally this big. I swear to freaking God, it was this big. Open up, sucker up. And it was all the scholarships. So this book was just like wasting cement of paper because like every month they would update it. A whole nother book would come. I'm like, oh my God, man. Anyway, so you open this book up and it says, okay, here, if you want some money, you must be a math major. Yes. And, oh, you must have taken this course. Yes. And, oh, you know, so I go through and the last one is, and you must be like 50% Scandinavian. I'm like, shit. So the and, that's another example of and reducing the number of things that match. Okay. So, let's see, I've got all that's good. Good. All right. So the observation was or is basically add, and is basically multiply. And now I want to show you a silly example and a serious example about and being multiplication. Let's do the serious example first. You guys know what happened in 1986, and it actually happened again, I forget what year it was actually, which I feel bad about. This happened twice, something related to the space program.
Challenger.
Yes, the space shuttle exploded. 1986, I'll never forget, I was in English class. I'll never forget, I'm sitting right near the door because I'd like to so I can get the hell out when the bell rang. Sitting in English class. I was in Florida, we would normally go out and watch the space shuttle take off. And for some reason we didn't that day. And I'm in there going, oh man, I wonder what's going on. And over the loudspeaker, they announced, I'm gonna start crying right now. They announced, space shuttle has exploded, or whatever they said. Instead of making it a little more tactfully, the space shuttle exploded, get back to your freedom. And oh my God, so I remember this moment because it was really deeply impactful. Does anyone know why the second shuttle exploded? Because enough of the heat tiles came off on when they went up. Then when they came back in, they exploded because of the friction with the atmosphere, right? Does anyone know why the first shuttle? Do you guys all know this? The two shuttles exploded. Some of you guys are like, I don't know. Yes, you know why the first shuttle exploded? I'm sorry.
I'm fairly sure I know why, because from what I heard, it was a collaboration between American and British scientists.
Oh no, you're thinking about the Mars climate.
Oh, that's the
survey.
one they missed.
That's the one that they used. They didn't use metric. They used
Yeah.
feet and such, and
they-
so it actually
they
fell
used
in.
both, and they never told each other what.
Yeah,
it
yeah,
was.
that was the Mars thing. Do you know about the shuttle, the first shuttle?
If I remember correctly, and again, I could be wrong about this because I've heard of many of them. It was either a coolant issue in which it leaked a little bit on the side of it, or it was an oxygen issue.
Okay. It was the oxygen fuel mixture. It was
Yep.
these things called O-rings. And what the O-rings do, and again, we're not going to suddenly start to learn aerospace, which is great for those who don't, and I'm sorry if you wanted to, I'm sorry. But what the O-ring did was it basically made sure the fuel was going in one direction. Is it good for fuel to go in one direction?
Yes.
Yes, okay. So why would we have several of them?
Fail-safe.
Fail-safe. If you live in a really bad neighborhood, do you have one lock on your door?
No.
No, you have several, right? The worse the neighborhood, the more there is. So in my life, I know this is really weird. Over time, I've noticed less and less locks on my door. Over time. When I was a grad student, dude, I lived in the basement thing with a hot water pipe going over, and I had about 6 locks on my door, dude. But you know, it's the way it goes. But I paid $325 a month. So hello. All right.
You don't need a lock, you just need to make it Home Alone style traps.
Yeah, exactly. Yeah. So, if you really, really needed to wake up, you had a really early final, do you set one alarm?
No.
No, you set multiple alarms, right? At least 2 or so, right? You guys kind of with me? So why do you do that? Because the probability of something failing is more than 0%. Therefore, we build in fail-safes, like you said. So let's say the probability, this is not true, but just for the sake of making this calculation easier, let's say there's a 1% chance that an O-ring will fail, right? If I add, like I do for OR, and I put multiple ones in, that would actually increase the probability of the whole thing failing, which doesn't make any sense. So think about it like this. 1% of the time, this one will fail, correct? 1% of those times, the next one would fail. So I've got 1% of the time this one fails, and 1% of those times this one will fail. Does anyone know what of means in mathematics? If I had 5 crates, right? If I had every crate has 8 apples, and I have 5 of those crates, how many apples do I have? Every crate has 8 apples, and I have 5 of those crates. 40. What's 1/2 of 8? That's why you think it's division, but isn't that 1/2 times 8?
Yeah.
Okay, so of means multiply. What is 0.01 times 0.01? 0.0001. And then I got a third one, correct? So already it went from 1 out of 100 chance to a 1 out of tens, hundreds, thousands, 10,000 chance, right? And if I add one more, hello, are you guys sitting with me? So if there's a 2% chance your alarm doesn't work, you're going to set another alarm. Now there's a 2% of 2% chance, which gets smaller, correct? You guys semi with me? I'm trying to show you why. So the only way this will totally fail is if this one fails, and this one fails, and that one fails. And the probability of that would be 0.01 times 0.01 times 0.01.
Wait, so did the challenger just use like one O-ring or something?
No. Here's the real thing that happened. That morning was cold, which reduced the viability of the O-rings. So the probability of failure went from like 0.000 whatever up to 0.2 or something insane. So they were, those were the days we had launched the Challenger. We were all like, look at us humans, we're amazing, holy shit. And we're like, yeah, we had just been getting lucky. We had been getting so lucky. And then that was when reality hit us in the face. Because we've been stupid lucky. And then people are like, oh. Anyway, sorry. Whole side note. Sorry. So yeah, that's the specific thing. It actually, the weather increased the probability of the O-ring failing because its integrity was compromised. Maybe. Okay. The silly example is, let's say that I want to join a fraternity, and to join this fraternity, I go through some very mild hazing, nothing like we've heard. What's going to happen is I got to walk down this hallway, and every third step I take, I get smacked on this cheek, and every fifth step I take, I get smacked on that cheek. How often will I get smacked on this and this cheek? No. Every 15th step. Yes? Does that make sense?
Yeah.
1/3 of 1/5 is 1/15th, right? So that's a silly example, I'm sorry. So that's just another example of why and. When will I get slapped on this and this at the same time? A little Home Alone thing going on. 1/3 times 1/5. Okay. All right, so let's do this. Oh, yeah, that's right. A couple more things, and then I've got a worksheet. Okay. Running out of time. Let me see. So far, we've been picking one thing at a time. So let me set up a thing here. Let's say in a bag, I've got 4 green marbles. I know. 5 blue marbles, and 11 white marbles, right? Classic statistics problem. Okay. It could be poker chips or whatever. Let's start off easy. If I pick 1 marble, what's the probability that I get a white marble? 11 out of 20. Which is what percent? 55%. All right, blah, blah, blah. I can ask you though, it's not very interesting. What if I pick 2 marbles? There's more information I have to give you. I picked 2 marbles, but I'm going to do it this way. I'm going to pick 1, record the color, drop it back in. So I'm going to do what's called with replacement. Okay. Pick 2 marbles with replacement. What's the probability I get a green and then a blue?
You would just add green and then blue.
Green
So
and
it would
then
be,
blue.
4 out of 20, and then.
So yeah, I think of it as a hangman game sort of. I have 2 things. One thing and another thing. Okay, I like it. This was probably the first thing is green.
4 to 20.
4 to 20, right? 4 to 20. And then I drop that back in.
5 to 20.
Anybody with me? The 4 to 20 is the green. And then I drop that back in. Now what's probably the next thing I get is blue. Yeah, 5 out of 20. I think it's 5%. Yeah. how does this jive with our formula for probability of A and B? It says probability of A times the probability of B given A, correct? I really want you guys to get this. And is basically multiplied. If I pick a green first, does the next pick give a shit about that? Does the next pick change because I picked a green first? No, because I dropped it back in, right? So what will happen then? So this is still the formula, because the probability I get a blue given that I got a green is the same as the probability I got a blue. Because it doesn't care. Nothing changed. But if I pick two marbles without replacement, come on, think. All right. What do I get then for probably green and then blue? Well, probably green is 4 out of 20, and then I feed that to my little brother, right? Or throw it away. Explains a little bit about this question. Oh, sorry, James. 4 out of 20 chance for the green. I throw it away. What's probably get a blue now? There's still 5 blue marbles, but there's only 19. Do you see how that's the probability of blue given that I picked a green already? I really want that. That's exactly the formula that we got earlier. But it only makes sense. Of course the bottom went down by 1 because we lost a marble. I've lost several. So, I don't know. It's going to be a little more than 5%. No idea what it's going to be. It's going to be 0.0512. Making this shit up. I don't know. Somebody help me out.
0.05.
What is it?
0.0526.
Oh, it's close. All right. 0.0526. Okay. All right, so let's do this. I am going to finally today, good Lord, Jeff, I'm going to finally shut the hell up. So let me point out something. There's a side that says this side in class. So guess what? That's what we're going to do right now. And then there's a side that says practice for test 3. This is the side I'm going to have an answer key for this, just like I'm going to have an answer key for the practice test tomorrow. So you can do this on your own time. I'll have the answer key tomorrow. Let me give you this. I kind of want to do this. So I'm going to let you get a little ahead of me, and then I'll catch up with you just for interest of time. I did not pace myself well today. So make sure you got this side that says this side in class. Can you guys go ahead and try to do ABC? And I'll catch up to you. Good Lord, you're right. Okay, there you go. Oh yeah, let's do that. Computer, hello. Oh, that's right. You died. I killed you. Okay. Poor little dude. All right, little dude, we can do this. Poor little guy's like, give me a second. All right, Alright, so I really hope this first problem is pretty straightforward. What's the first thing you guys are doing? I'll start to catch up.
Filling out the contingency chart.
Yeah, so see what I did? I left all these blank spots, so I was hoping to kind of like jog your memory. First thing you want to do is add all these up. I think that's what that is. Is that right? Yeah. Bless you. And something strange that happens sometimes, each of these questions is completely its own question. It's not dependent on what came before, you understand? So it's like you're starting all over for each question. So who's got the probability that I pick a person from this group that attends Grossmont? Give me the ratio first, sorry.
126 by 176.
126 Grossmont attendees out of 176 students. Yeah. And then
Roughly 7%. It was 7.15.
7,
159.
159, okay. Doobie doobie doo. All right, now somebody else help me out with probability we pick a business major.
92 divided by 176.
So somebody else means someone that I haven't heard from yet. 92 out of 176. Has everybody got that? Okay.
0.5227.
0.05227, so 23, like that?
No,
Or 0.5, yeah, because it's more than half, Jeff. There you go. 5237?
227.
227, thank you. I'm not good with numbers. So computers, now here we have our first little, thing we got to be careful about. So let's see, somebody else, tell me. Computer science major or attends Grossmont.
Would be 73, and then plus 64.
73 plus, oh, I see what you did, okay. And I would, or I would do 126 people attend Grossmont plus the 11 computer science, or you could do the formula, which is 126 Grossmont plus 73 computer science minus 62 Grossmont. And well, why would you do that shit, right? So if I count all the Grossmont students, there's only 11 computer science people I have not counted yet. I really want you guys to see that. So how many people match what I'm looking for? 137, right? Out of still 176. The only time the bottom won't start off as 176 is if I give you something. Yes?
I think I'm just confused how you got the 137.
Oh, okay, so two ways. If I do, I'm sorry. Oh, yeah, okay. If I do Grossmont students plus computer science, I then have to subtract the 62 people who are both. Or I could do 126 Grossmont, so I've already counted them, plus the 11 computer science that I haven't counted yet. So that's 137. Both ways will give you 137. I really want to see that. Because real quick, 126 plus 73 minus 62, well 73 minus 62 is 11. So you just do 126 plus 11. Yeah.
I just wanted to know if when we're given a probability, can we leave it as a fraction, or do you want us to give the?
Oh, I always want the 4 decimal place
Okay.
answer. And then you can make that a percentage if you want to. Fraction's not enough. In fact, I mean, if somebody told me that's the probability of me getting it, I'm like, what is that? You know what I mean? Yeah, I as a human, we want to know the percentage. So what is this if you do a decimal? 7784? Okay, thank you. In stereo. And you can make that 77.84. Beautiful. In fact, on the test, I'll put your answer should be 4 decimal places for the probabilities. Yeah. Okay. Then we have an and coming up. Do I need to use the formula that we created? Shit, no. In fact, the formula would make this so terrible. This is very straightforward. How many people match being a math major and a Cuyamaca student? 2 people. Only 2 people match both, right? Out of how many total people? 176. And then, whatever the hell that is. 0.0 113? Okay. All right, now nobody say anything. Look at part E. Try to construct that ratio. So what's going to go on the bottom? Yeah, because we're talking about computer science majors. We know that the person I'm looking at is a computer science major. Out of those 73, how many match what I'm looking for? 62. Let's see, it's like 0.86. 49. No? What? No. Oh, 8493, yes. Sorry, I thought I should. 0.493. So wait a minute. Okay. Let me stop for a minute. Is this doing okay so far? Okay, okay. Yes? Oh, why aren't we? Because I don't have to. I don't want to. That's why I say you can if you want to. Right? Yeah, totally. But I at least, so I have a shirt again. I haven't worn it yet because, to be honest, I haven't found it. Shoot. But it says show your work, right? I know why, because it looks really evil. I want to get one that's a little less evil. So to me, the work is the most important thing is your work. So when you're doing this kind of problem, it looks like we haven't done a lot. This is your work. This is the answer. The work is constructing the ratio. So if you only put down the decimal or something, I'm going to take points out because I don't see any work. Okay. So you can make this a percentage if you want to. Now here's something new. I want to get your take on this question. We haven't talked about this yet, but I want to just see what you guys think. Are being a Grossmont student and a computer science major independent events? So are being a Grossmont student, being a computer science major, are they independent?
I said no because it can infer that maybe the computer science program is better and corresponds to such a
Oh.
larger portion of the ANACA.
Portion is a good word. There's specific work we've done. And again, I didn't talk about this idea, so it's a little bit mean. But again, I'm not grading this, so who cares? Yes.
I would say yes because you can be one without the other.
Okay, I got it. So here's what independent means. To be independent, one thing should not care what the other thing does. Would you say that that's a decent, real quick, simple definition of independent? Okay. So, if I know they're a computer science major, does the probability they're a Grossmont student change?
Yes.
The probability they're a Grossmont student is 72% roughly, yes? If I know they're a computer science major, the probability of a Grossmont student jumps up. Which kind of is what you're saying. If I see that, I'm like, oh, there's just, Grossmont's got a bigger computer science thing, maybe. Maybe that's what they mean. And again, this is a sample, but still. I really want this to make sense. The only way two things can be independent is if one happens and the other one doesn't give a shit. So if I told you, oh yeah, they're a computer science major, and the probability stayed 0.7159, they would be independent. One happened and the other one didn't care. Right? I really want this to make sense. So the way to check if two things are independent is if the probability of the given is that the same as the probability by itself. I really want this to make sense. If independent means one does not affect the other one, what's the only probability where we bring into play something changing, given. So if I'm given that B happened and A doesn't care, it stays the same, they are independent. But that's not what happened here. These weren't equal to each other. So no, they're dependent. The probability of it being a gross student depends on if they're a computer science major or not. And we can see it, the number changes. Right, it goes up. Yes?
Could you, because I, didn't even think to look at the percentages, I just more looked at the.
Oh yeah, the numbers, you sort of intuitively can tell.
Yeah,
But this is a much more,
but it's more precise.
yeah, because the numbers could kind of be misleading just glancing at them. This is more precise, yeah. But I appreciate what you're saying. You can kind of tell. This is a small sample. We can kind of see. Okay, maybe. Yes.
Can you repeat that? The probability of the given must be equal to the estimated?
Just the probability of the original. So if the original probability doesn't change when I'm given something else happen. So the probability you get to school on time, is that independent from the traffic? Are those independent? No. Given that there's insanely bad traffic, the probability you get to school on time will go down, correct? Did I just say that if the traffic is bad, you won't make it to school on time? No, I just said the probability changed. Some people get hooked up on, well, one doesn't need the other one. No, does the probability change, right? I got in trouble for this one, so let me just do it again. Hopefully, I want to point something out. If I see off in the distance somebody walking towards me, and they're really far away, I can't tell if it's a man or a woman yet. I just can't. They're way too far away. I can't tell. So the probability is a man or woman 50%. Would you agree? Okay, because it's roughly 50-50. Nature actually gives more boys because men tend to die earlier, and nature somehow actually kind of averages that out, believe it or not. Okay. If off in the distance I saw this person get off of a Harley Davidson motorcycle. Now here's where I got in trouble with somebody. It's really funny. The probability it's a dude. Did it stay the same? Go up or go down? Goes up. Did I just say that no women ride Harley Davidson motorcycles? No, this is a probability question, correct? Okay, because I remember I had this one woman, she's like, I drive Harley Davidson. I'm like, no, I didn't say nobody, I didn't say that. It's a probability question, yes? Do you guys so they would not be independent. If I knew a person, something about a person, that would change the probability that they do blank, correct? You guys kind of with me? A little bit? Okay. Doesn't mean that they definitely do blank. It just changes the probability. Okay. I love it. All right, so, yeah. Let's do one more thing here. Okay. Look at number 2. Now these first two should be really quick, right? So this is something we might all like to do at some point. Just throw a bunch of politicians at a freaking haunted house and let them scream. Be a little cathartic.
Scream or make money?
Huh?
Scream or make money?
Somehow they'll make money out of it, I'm sure. If I pick one person out of that haunted house, what's the probability to pick a Democrat?
7.
Yeah, because how many people are in there? 21. So 7 chances to get a Democrat out of 21. Real quick, I will get somebody tell me the answer is 1 out of 7. Why would somebody say the answer is 1 out of 7? It is not 1 out of 7, but can you understand the logic? I'm going to get somebody tell me, I always do, that to probably get a Democrat is 1 out of 7.
Because they reduce the population.
The way they look at it is there's 7 Democrats and you want to get one of them. It doesn't make any sense. Probability is all about how many chances do I have to get something to happen. So I have 21 things that could happen. 7 of them match what I'm looking for. Okay. And that is 1/3, so 0.3333. What about the person's Republican?
12 out of 21,
Yeah, 12 Republicans out of 21.
15714.
Yeah. And then these two are the question about with replacement. I'm going to pick 2 people. So the minute I see this kind of problem, I'm going to pick 2 people. One person, time, because and means times, another person. So the first person I want is an independent. What's the probability of that? 2 out of 21. I put them back in the house, right? They're like, oh, thank you. And I shove them back in the house, and they go screaming. And then what's the chance that I get the next person as a Republican?
12 to 21.
Yeah, everything stays the same because I put that person back in, correct? Okay. And then you just have to multiply those out, whatever the hell that is. 0.056 something.
I got 0.0541.
Okay. I think you're pretty close from my head.
And then.
Now, real quick. If I do this next one, see how I kind of like to do this where the questions are the same. It's just now I'm doing it without replacement. What would have changed? The first person being an independent,
21.
still 2 out of 21, but now I let them leave. What's probably I get a Republican now.
12 to 20.
Yeah, there's still 12 Republicans in the House, but there's only 20 people in there now. Do you guys see that? If I pick somebody and then I let them go, I don't replace them, I don't put them back in. Now there's one less person in the House, right? All right, so I'll tell you this. I think that's enough. Next time, we'll finish this worksheet out together. In the meantime, I know you have, with all the time that you got a ton of time. You know, no, I'm joking. I'm so joking. You got a lot of homework to do. But this side, I will have an answer core. I'll have an answer core for this I'll have an answer key for this tomorrow. And I'll have an answer key for the practice test. Okay. Well, I think that's plenty for today. We'll see. Hopefully you guys all come back. We'll see. Yes.
I was gonna say it's 0.057.
Yes, 0.057, yes, because it's like basically 571, right? It's basically 1/10 of this guy. Yeah. Cool. Oh, sweet.
And then I had a quick question with this, with number 3 of B,